Welcome! In this multivariate calculus tutorial, we are going to calculate the gradient vector, the directional derivative, and we're going to do some basic calculations in Lagrange multipliers because that's a direct application of the gradient vector. Okay, so let's get started here with question 1. So in question 1, we're asked to calculate the gradient vector f, evaluate grad f at the point P, and find the rate of change of f at P in the direction of the vector u. Now that last one, the rate of change of f at P in the direction of the vector u, that is given by this formula right here, the directional derivative. Okay, so let's begin. We have f is a function of x and y, and it's just x over y, which we can also write as x times y to the minus 1. Okay, we have the point P equal to 2, 1, and then we have the vector u, which in this case happens to be a unit vector. Now I will write this 1/5 of the vector 3, 4. And this is the way I write it, but some people put angled brackets for vectors. Now I like to say that these look the same in their representation there, but they're different because this is a vector and this is a point, and we understand that through context. Okay, notice I put a tilde under this one and I don't with a P. Okay, so we've got all this. Now first let's calculate the gradient vector. So grad f is the vector given by fx, fy, where fx is the partial derivative of f with respect to x, and fy is the partial derivative of f with respect to y. So let's calculate this, differentiating x y to the minus 1 with respect to x, and differentiating x y to the minus 1 with respect to y. Okay, so that y to the minus 1 can go through the operator because we're differentiating here with respect to x. And the derivative of x with respect to x is 1. So we have y to the minus 1, and then over here we are differentiating this with respect to y, and so the x can float through the operator. And so we're differentiating y to the minus 1 with respect to y. So we pull down the minus 1 and subtract 1 from that exponent. So we have minus x y to the minus 2. Okay, so this is our gradient vector at x, y. All right, so now the question asks us to evaluate this at P. So grad f at P is grad f at 2, 1. And so we're just substituting in here x is 2 and y is 1. So we have 1 to the minus 1 minus 2 times 1 to the minus 2. And so this is 1, minus 2. Okay, so the next thing we're asked to calculate is the directional derivative. So this is f subscript u evaluated at P. And so this is given by the formula grad f 2, 1, and then this is a dot product of the vector u divided by the norm of u. All right, but here you can see since 3 squared plus 4 squared is 5 squared, the norm of the vector u is 1 because in the numerator, the square root of 3 squared plus 4 squared is 5. And then in the denominator, we have the square root of 5 squared, which is 5. So 5 over 5 is 1. So the norm of u is 1. Okay, and so we use the letter u here. Now this comes out of the book by Stewart. Presumably, they're writing u for unit vector, but I don't want you to think that way. I think it's better to use this formula because you might encounter a vector that is not a unit vector, and so this is the correct formula for that. All right, so let's simplify this. So we already have grad f at 2, 1. It's the vector 1 minus 2, and then we take the dot product with u over the norm of u, which is 1. So now let's simplify this. Now, since this is a dot product or scalar product, we can take this scalar multiple and bring it all the way out the front. So we have 1/5, 1 minus 2 dot 3, 4. All right, so let's simplify this. We have 1/5 of 1 times 3 plus minus 2 times 4. And so that's 1/5 of 3 minus 8. So that's 1/5 of minus 5, and that's minus 1. Okay, so the directional derivative of f at P in the direction of the vector u is minus 1. Now what is that? That's a slope of the surface in the direction of the vector u. So if you want to see more details on the geometric point of view of that, have a look at my lecture video on this same topic. So multivariate calculus, and I forget which lecture number, but you can find it. Okay, so let's move on to question 2. So in question 2, we're doing the same thing, but with a different function, a different point, and a different vector. Okay, so here in question 2, we've got a function of x and y. It's given by x squared times the natural log of y. In mathematics, when we write log, we tend to mean the natural log, the point 3, 1, and the vector 1/13 of minus 5, 12. So first let's calculate grad f. And so we are differentiating with respect to x, this function x squared natural log of y, differentiating with respect to y, x squared natural log of y. Okay, so simplifying this, natural log y does not have an x in it, so we can treat this as a constant, pull it out the front, and differentiate x squared with respect to x. So we'll get 2x for that. And so the x component of this gradient vector is 2x natural log of y. Okay, now differentiating x squared natural log of y with respect to y, the x squared can come out. And so we're differentiating natural log of y with respect to y, and that, of course, is 1 on y. So we get x squared over y for this part. All right, so next we're going to evaluate this gradient vector at the point 3, 1. So grad f at 3, 1. So substituting in x is 3 and y is 1. We have 2 times 3 times the natural log of 1, and then the y component is 3 squared over 1. Okay, so what do we get? We have 6 times the natural log of 1, but e to the power of 0 is 1. So this is 6 times 0, which is 0. And then over here we have 9 over 1, which is 9. So 0, 9. All right, so now for the directional derivative, f subscript u at the point 3, 1 is grad f 3, 1 dot the vector u over the norm of the vector u, and I'm just going to leave it like this because you can clearly see that the norm of the vector u is 1, because, isn't that right? Okay, so minus 5 squared is 25. 12 squared is 144. 144 plus 25 is 169. When you take the square root of that, you get 13. So this vector u is a unit vector. It has norm 1. So this denominator is dividing that by 1. Okay, so simplifying this then, we have 0, 9 dot 1/13 minus 5, 12. Pull the 13 out the front because that's a scalar multiple, and we have a scalar product, 1/13. Then in brackets, 0 times minus 5 plus 9 times 12. Okay, so this is 0. 9 times 12 is 90 plus 18, so 108. So we have 108 over 13. All right, let's move on to question 3, and I'll scoot this up so you can see it. Okay, so in question 3, we have a function of x, y, and z. So you can see x, y, and z appear in this function. We have the point, it's a 3-dimensional point, 3, 0, 2, and we have a vector in 3 space, 1/3 of 2 minus 2, 1. All right, so function point vector. Okay, so the gradient vector in this case, it's fx, fy, fz. And so here we need to differentiate the function f with respect to x, then with respect to y, and then with respect to z. Okay, so differentiating this with respect to x first, e to the power of 2yz is treated as a constant when we're differentiating with respect to x because it doesn't have any x's in it, so we can pull that through the operator and just differentiate x with respect to x, and we get 1 for that. So the x component of this is e to the 2yz. All right, now differentiating this with respect to y, the x can come through the operator, and so we differentiate e to the 2yz. So let's simplify this as x times the derivative with respect to y of e to the 2yz. And then here, same thing, the x can come through the operator, and we are differentiating e to the power of 2yz with respect to z. Now, each of these two require the chain rule. All right, but we can do that in our heads quite easily if you're familiar with the process of differentiation. You might want to review the previous tutorial on taking partial derivatives. So we have e to the 2yz as the x component. Now we'll treat that exponent, let's call it u. So the derivative of e to the u with respect to u times the derivative of u with respect to y using the chain rule. Now the derivative of 2yz with respect to y partially is 2z. So an extra 2z comes out, and so we have 2x times z then e to the power of u. And so this is what we get there. All right, so same thing here, but with respect to z this time. So a 2y comes out. So we have 2x, y, e to the power of u, but u is 2yz. Okay, and so here is our gradient vector, grad f at x, y, z. Okay, now taking that point 302, subbing it in where we see x, y, and z, grad f at 302, we have e to the power of 2 times 0 times 2. Then we have 2 times 3 times 2, this part, e to the power of 2 times 0 times 2. And then for this, 2xy is 2 times 3 times 0, and then e to the power of 2 times 0 times 2. Okay, simplifying this, here we have e to the 0, which is 1. 2 times 3 times 2 is 6 times 2, which is 12, times e to the 0. So 12 times 1 is 12. And then over here we have 0. I shouldn't have a comma there. Get rid of that. Okay, so 1, 12, 0. All right, so that's our gradient vector at the point P. So now let's calculate the directional derivative at P. And so remember, we have a formula for this. It's grad f at P dot u over the norm of u. Okay, now I'll bet you this vector u is a unit vector, but let's just check. So the norm of u is the square root of 1 over 3 squared, brackets, 2 squared plus minus 2 squared plus 1 squared. Now, in my bracket, but I'm out of paper there. All right, so inside this bracket, we have 4 plus 1, which is 9. 9 over 9 is 1. So this norm is 1. So u is a unit vector. Again, let's just think of it as a coincident. Okay, so simplifying this, the gradient vector is 1, 12, 0. And then we're dotting this with the vector 1/3 of the vector 2, minus 1, minus 2, 1. Okay, the 1/3 can come out in front. And so then we have 1 times 2 plus 12 times minus 2 plus 0 times 1. Okay, simplifying that, that's 1/3 of 2 minus 24. And so we've got 1/3 of minus 22. So minus 22 over 3. All right, question 4. So we have a function of x, y, and z. It's x plus y times z to the power of a half. Now notice this is not quite what you see there on the PDF on the left, because there it's written the square root of x plus y times z. Now that's the same thing as this, but this is an aid to memory to tell you what do with the derivative. So it's better to put it in this form, because then you're reminded of how to differentiate u to the power of a half. You bring down the half, you subtract 1 from the exponent. All right, so first let's calculate grad f. So we have f x, fy, fz. Okay, and so we're differentiating with respect to x, x plus yz to the power of a half. Same thing with respect to y, and then with respect to z. All right, so you can see that we need to use the chain rule here. So I'm going to set this out with a little bit of space. Okay, so here you can see I've written out each of these derivatives using the chain rule. And so here you might think of u as x plus yz. So this is du to the half with respect to u times du on dx. And then similarly with respect to y and with respect to z. I've set out the chain rule. All right, so now let's simplify this. The derivative of u to the 1/2 with respect to u, and so I'm just going to draw an arrow and say u is x plus yz. But this derivative is 1/2 u to the 1/2 minus 1. So we have 1/2 u to the 1/2 minus 1. Okay, and then it's multiplied by the derivative of u with respect to x. In this case, it's 1. Just put times 1 there. Okay, next, taking the derivative with respect to y partially, again, we have 1/2 u to the 1/2 minus 1. And then times the derivative of x plus yz with respect to y partially, and so that is just z. And then similarly here we have 1/2 u to the 1/2 minus 1, and then times the derivative with respect to z of x, y times z. And so that is just y. All right, so simplifying this, we can write this one as 1 over 2 u to the 1/2, okay, because 1/2 minus 1 is minus half, and then we can bring it down to the denominator. And similarly, the second component is z over 2 u to the 1/2. And the z component of this gradient vector is y over 2 u to the 1/2. Okay, now substituting in u is x plus yz, and let's also write this as a square root because in the PDF it's presented as a square root. So we have 1 over 2 times the square root of x plus yz, and then z over twice the square root of x plus yz, and then y over twice the square root of x plus yz. Okay, now because this has got this same square root in the denominator and the 2 is common as well, we can pull this out as a scalar multiple and simplify the look of this. So let's write grad f at the point x, y, z is 1 over 2 root x plus y times z, and then multiplied by the vector 1, z, y. All right, so now in this little remaining space, we can easily put what grad f at p is. Grad f at 131 is 1 over twice the square root of 1 plus 3 times 1, and then multiplied by the vector 1, 1, and 3. Okay, so simplifying this, in the denominator, we have 1 plus 3 square root. The square root of 4 is 2. So 1 over 2 times 2, that's a quarter. We have 1/4, 1, 1, 3. Okay, now let's take another page and write our last part of this question, which is to calculate the directional derivative or the slope of the function f at the point 131 in the direction of the vector u. So we had grad f at p dot the vector u over the norm of the vector u. So let's calculate the norm of the vector u. So we have the square root of 1 over 7 squared, 2 squared, plus 3 squared, plus 6 squared. So simplifying this, we have 1 over 49. The square root of that is 7. So 1/7 of 4 plus 9 plus 36. 4 plus 36 is 40. 40 plus 9 is 49. And then when we take the square root of that, we have 7. So this is 7 over 7, which is 1. So the norm of u is 1. Okay, so grad f at p, we've worked that out to be 1/4 of the vector 1, 1, 3. And so then we dot this with the vector u over the norm of u. So 1/7, 2, 3, 6. Okay, now pulling that scalar out the front, we have 1 over 4 times 1 over 7, which is 1 over 4 times 7. 7 times 4 is 28. So 1 over 28, 1 times 2 plus 1 times 3 plus 3 times 6. So this is 1 over 28, 2 plus 3 plus 18. 18 plus 2 is 20. 20 plus 3 is 23. So we get slope 23 over 28. Okay, question 5. We've got g is a function of both s and t. S t to the 1/2. P is the point 2, 4. V is the vector 2, -1. So here I would expect that that vector does not have norm 1. So it's not a unit vector. So we do have the norm of u dividing by this, and it's not 1. Okay, so let's begin by taking grad g, and so we're differentiating g partially with respect to s, differentiating g partially with respect to t. So, okay, so t to the 1/2 is treated as a constant, so that flows through the operator, and then we differentiate s with respect to s and get 1 for that. So then we just have t to the 1/2 in the s component. Okay, differentiating with respect to t, the s can come through the operator. And so differentiating t to the 1/2 with respect to t, the 1/2 comes down. Then we subtract 1 from the exponent. Okay, so simplifying this, we can express this gradient vector as the square root of t, comma, then we have s over 2 t to the 1/2, so s over 2 root t. Okay, so now let's take grad g at the point p, so 2, 4. So we're subbing in s is 2 and t is 4. So we have the square root of 4, and then 2 over 2 times the square root of 4. So we have 2. And then 2 over 2 times 2. So 2 over 4 is 1/2. Okay, so next, let's calculate the directional derivative. So g subscript v at p. So we have grad g at 2, 4. and then we dot 1 over the norm of v times the vector v itself. Okay, and so let's calculate the norm of v. So we have the square root of 2 squared plus minus 1 squared, and so 2 squared is 4, minus 1 squared is 1, 4 plus 1 is 5, so this is 1 on root 5. Okay, and so then grad g at 2, 4 is 2, 1/2, so 1 on root 5, 2 comma 1/2 dot 2 minus 1. All right, so simplifying this, we have 1 on root 5 times 2 by 2 plus 1/2 times minus 1. So that's 4 minus 1/2 over root 5. So 4 minus 1/2 is 3.5, which we can express as 8 minus 1 all over 2. So 7 over 2, and then that's all over root 5. Okay, so we can tidy this up quite a bit by multiplying numerator and denominator by root 5. And so we get root 5 over 5 for that. So we can call this 7 over 2 by 5 times root 5. And so that's 7/10 of root 5. Okay, moving on to question 6. Okay, so we have a function of x, y, and z. X squared y plus y squared z. We have a point P, which is 1, 2, 3. And then we have a vector v, which is 2, minus 1, 2. So let's begin with grad f. So we have fx, fy, fz. So this is the partial derivative with respect to x of x squared y plus y squared z. And then partial derivative of f with respect to y, x squared y plus y squared z. Partial derivative with respect to z of x squared y plus y squared z. Okay, simplifying each of these derivatives to form our gradient vector. So differentiating this with respect to x, the y can go through the operator. The derivative of y squared z is 0 with respect to x partially. And so we just have x squared for that. Okay, now differentiating x squared y plus y squared z with respect to y partially, the x squared can come through. And so we have x squared plus 2yz. Differentiating with respect to z partially, we have 0 plus y squared, so y squared. All right, so now we've got the gradient vector. So now we want to evaluate the gradient vector at the point P. So we're subbing in the point 1, 2, 3. So we have 1 squared in the x component. Then we have 1 squared plus 2 times 3. And then we have 2 squared. And so we get 1 plus 12 is 13. 2 squared is 4. So grad f at P is the vector 1, 13, 4. Okay, now for the directional derivative, which is the slope of the function f in the direction of the vector v at the point P. So we have 1, 13, 4. Dot 2 minus 1, 2 over the norm of 2 minus 1, 2, which is the square root of 2 squared plus minus 1 squared plus 2 squared. So simplifying this, that norm there is the square root of 4 plus 1 plus 4, which is square root of 9. The square root of 9 is 3. So move that 1/3 in front. And then in brackets, we have 1 times 2 plus 13 by minus 1 plus 4 times 2. So 1/3 of 2 minus 13 plus 8. So 10 minus 13 is minus 3 over 3. And so we get a slope of minus 1. Okay, question 7. So in question 7, we have a function of x, y, and z. X e to the y plus y e to the z plus z e to the x. We have a point 0, 0, 0 and a vector 5, 1, minus 2. Okay. Grad f. Okay, so here we have grad f. And so simplifying this, we need to differentiate that function f with respect to x, with respect to y, and with respect to z partially, respectively. So this first piece of it has x e to the y. Now e to the y can be treated as a constant. So this is e to the y times the derivative of x with respect to x, which is just e to the y times 1, so we have e to the y. There, the derivative of y, e to the z with respect to x is 0, and then we have z times the derivative of e to the x with respect to x, which is just e to the x, so z e to the x. Okay, moving on to the derivative with respect to y, we have x e to the y plus e to the z plus 0. With respect to z, we have 0 plus e to the z plus 0. No, plus e to the x, okay? And so let's write this e to the y plus z e to the x, x e to the y plus e to the z, e to the x plus e to the z. Okay, now substituting in that point P, we have e to the 0 plus 0, 0 plus e to the 0, e to the 0 plus e to the 0. And so this is 1, 1, 1 plus 1 is 2. Okay, and so now let's calculate the slope of the function f in the direction of the vector v at the point 0, 0, 0. So grad f at p, we've worked out that that's the vector 1, 1, 2. Then we have the vector 5, 1, minus 2 over the norm of 5, 1, minus 2. Okay, so simplifying that norm, we've got 25 plus 1 is 26, plus 4 is 30. So the square root of 30 there. And then 1 times 5 is 5. 1 times 1 is 1. And then 2 times minus 2 is minus 4. Okay, 6 minus 4 is 2. So 2 over root 30, which we can express as 2 root 30 over 30, which is root 30 over 15, rationalizing the denominator. Question 8. We have a function of x and y given by 4x to the 1/2 times y and a point P, which is 4, 1. And so this question asks, find the maximum rate of change of f at the given point and the direction in which it occurs. So what we want to calculate here is grad f at p. This is this gives the vector in which we should go to ascend that surface most rapidly, but the maximum rate of change of f is the norm of that, okay? And so let's calculate this. We first need to calculate grad f, so that's the derivative of 4x to the 1/2 y with respect to x at the point 4, 1, and then similarly differentiating with respect to y, and then evaluating that at the point 4, 1. So differentiating this function with respect to x, we bring down the 1/2, we subtract 1/2 from the exponent. So we have 4 times 1/2, x to the minus 1/2 times y, evaluated at 4, 1. Okay, now differentiating this with respect to y, the 4x to the 1/2 can go through the operator because we treat the x as a constant, and differentiate y with respect to y, and we get 1 for that. So 4x to the 1/2 evaluated at 4, 1, and then we are going to take the norm of this. All right, so continuing, 4 divided by 2 is 2. Then we substitute in 4 for x, so that's 2 over the square root of 4. 2 for this part, the square root of 4, and it goes down the bottom for the denominator. And then we multiply by y, in this case the y is 1. Okay, now over here, this is 4 times the square root of 4. So simplifying this vector, which is the gradient vector, so we have 2 over the square root of 4. Now the square root of 4 is 2, so 2 over 2 is 1. 4 times 2 is 8, and then we take the norm of this vector. We have the square root of 1 squared plus 8 squared, and so 8 squared is 64, 1 squared is 1, so the square root of 65. Okay, and so this is the maximum rate of change of f at the point P. Now, which direction does it occur? It occurs in the direction of the vector grad f at P, and so this is 1 on root 65 to express this direction as a unit vector, and then we found the vector 1, 8, which is grad f at P. Okay, so that completes question 8. Let's move on to question 9. We have a function of x, y, and z, and so we can express this as 1 over z times x plus y, and then the point P is the point 1, 1, minus 1. All right, so we know we're going to need fx, fy, and fz, so let's calculate. So the 1 on z can come out the front, and so for this, we just get 1, and then times 1 on z, so 1 on z for that. Okay, differentiating with respect to y, similarly, we're going to get 1 on z. differentiating f with respect to z is a little bit different. So this time the x plus y could come out in front because it has no z's in it. And we are differentiating with respect to z to the minus 1. So we pull down the minus 1, subtract 1 from the exponent, so we have z to the minus 2. And so we can write f subscript z equals minus in brackets x plus y over z squared. So this gives us gradient vector. Grad f is fx, fy, fz, which is the vector 1 on z minus x plus y over z squared. And now grad f at p, so this time we're just subbing in 1, 1, minus 1 for x, y, and z respectively. So we have 1 over minus 1, 1 over minus 1, minus 1 plus 1 over minus 1 squared. So this is the vector minus 1, minus 2 over 1 is minus 2. Okay, so now we have grad f at p. So to find the maximum rate of change of f at the point p, we need to take the norm of this vector. So the norm of grad f at p is the norm of the vector minus 1, minus 2, which is the square root of minus 1 squared plus minus 1 squared plus minus 2 squared. So the square root of 1 plus 4 is the square root of 6. So this is the maximum rate of change of f at the point P. And so which direction does this occur? It occurs in the direction of grad f at P, but you want to express that as a unit vector. Okay, so let's simplify this. So we have 1 on root 6 times the vector minus 1, minus 2. Let's just simplify by rationalizing the denominator and pulling out a minus sign. So we have minus root 6 on 6 times the vector 1, 1, 2. There we go. So in question 10, we have a function of the two letters x and y, and it's given by sine of x times y. I shouldn't have a comma there. And we have the point, p is the point 1, 0. Okay, so f subscript x is the partial derivative with respect to x of sine of x times y. And so we need the chain rule for this, letting u equal x times y. So we're differentiating sine of u with respect to u, but u is x times y. And we multiply by the derivative of u with respect to x. U is x times y. Say letting u be equal to x times y. Okay, so simplifying this, the derivative of sine of u with respect to u is cos of u. So we have cos of x times y, and then the derivative of x times y with respect to x partially is just y. Let's put that y in front so it looks better, and so this is f subscript x. All right, now for f subscript y, we're differentiating with respect to y sine of x times y. And so again, we need to use the chain rule, but in this position, we'll have a y. So simplifying this, again, we have sine goes to cos. So cos of x times y, and then times x. Let's put the x in front. So this is f subscript y. Okay, so now we can form the gradient vector at the point xy. So grad f at xy is the vector fx, fy, so y cos x x times y, and then comma x cos x y. Now to simplify this, we can see that in both components there's cos xy common, so we can pull that out. The cos x times y times the vector y comma x. Okay, so now grad f at the point P is cos of 1 times 0, and then times the vector 0, 1. So 1 times 0 is 0, cos of 0 is 1, so we just have the vector 0, 1. Okay, and so finally, the maximum rate of change of f at the point P is the norm of this vector, grad f at P, which is the norm of the vector 0, 1. And so that's the square root of, what have I written there? I'll cross that out. So that's the square root of 0 squared plus 1 squared. So the square root of 1 squared is just 1. Okay, and so this is the maximum rate of change at P. Now, which direction does it occur? It occurs in the direction of the vector 1 on the norm of grad f at p times the vector grad f at p. So because 0, 1 is just a unit vector, that is in the direction of the vector 0, 1. Okay, and so that completes question 10. All right, question 11, we have the temperature at a point xyz is given by 200 e to the power of this function of x, y, and z. The point p, 2, minus 1, 2, and then we have a vector. Now let's read this carefully. At the point p in the direction towards the vector 3, minus 3, 3. So that's the vector pq, where q is 3, minus 3, 3. Okay, so we need to take some care when it comes to calculating that vector. So part 1, find the rate of change of temperature at the point p in the direction towards that point q. Okay, so this is a directional derivative, and so we need to begin by calculating tx, ty, and tz, and hence calculate grad t. So tx is 200 times the derivative with respect to x of e to the power of u, where u is that exponent, minus x squared minus 3y squared minus 9z squared. So we need the chain rule for this one. So 200 derivative of e to the u with respect to u times the derivative of u with respect to x. Okay, and so simplifying this derivative, the derivative of e to the u with respect to u is e to the u. And differentiating this with respect to x, we get minus 2x. We can bring that minus 2x out in front. So minus 2 times 200 is minus 400. And then times e to the u, but u is this. Okay, so there's t subscript x. So t subscript y, similarly, okay, so we have this, and now the derivative of e to the u with respect to u is just e to the u. The derivative of this function of x, y, z here with respect to y partially is 3 times 2, so minus 6y. And then so we can bring that minus 6 together with the 200, so minus 1200y times e to the u. And so there we have t subscript y. Okay, now t subscript z is the partial derivative with respect to z of e to the u. So using the chain rule, we differentiate minus x squared minus 3y squared minus 9z squared with respect to z partially. So 9 times 2 is 18. So this derivative here is minus 18z. 18 times 2 is 36. So minus 3600 z e to the power of u. U is minus x squared minus 3y squared minus 9z squared. Okay, so these three, this, and this, give us the gradient vector. So grad t is the vector tx, ty, tz. Now each of these have in common e to the power of u, so let's pull that out in front. Okay, and so what else is common? Looks like we can pull out a minus 400 as well, and so that would leave here an x, it would leave a 3y, and then it would leave 9z. Okay, and so next what we need to do is evaluate this gradient vector at the point P, because we're seeking the directional derivative. So minus 400 e to the power of minus 2 squared is 4, minus 3 times minus 1 squared is minus 3, minus 9 times 2 squared is minus 9 times 4, so minus 36. And then we have 2 minus 3, 9 times 2 is 18. Okay, so simplifying that exponent, minus 43, and there we have the gradient vector at P. Okay, so now we've completed we have not completed part 1 yet, because we need the vector v. So let's say let v be the vector from P to Q, and so this is the point Q minus the point P taken as a vector once we take that difference. So we have 3 minus 3, 3, subtract 2 minus 1, 2. And so V is the vector 3 minus 2 is 1. Minus 3 plus 1 is minus 2. 3 minus 2 is 1. Okay, and so then the directional derivative T subscript V at the point P is grad T at P dot V over the norm of v. Okay, so now the norm of v is the square root of 1 squared plus minus 2 squared plus 1 squared, which is the square root of 1 plus 4 plus 1, so root 6. So let's put this root 6 in front, and then grad t at p is this vector, so times minus 400 e to the minus 43, and then times 2 minus 3, 18. Then we dot this with 1 minus 2, 1. Okay, so simplifying, minus 400 over e to the 43 root 6, and then we have 2 times 1 plus minus 3 times minus 2 plus 18 times 1. Okay, so 2 plus 6 plus 18 is 26. So minus 400 times 26 over e to the 43. Now let's write 1 over root 6 as root 6 over 6. Okay, so we can multiply this out and cancel a 6 where possible. So 26 has a 2 in it. We have minus 400 times 13 over 3 e to the 43 root 6. And so 400 times 13, well, let's consider 4 times 13, so 52, so 5200, so minus 5200 over 3 e to the 43 root 6. Okay, so next part of this, which is question 11, part 2, in which direction does the temperature increase fastest at P? So in the direction of the vector, grad T at P, and if you want to give a unit vector, it would be grad T at P over the norm of grad T at P. Okay, and so we have calculated grad T at P to be the vector minus 400 e to the minus 43 times the vector 2 minus 3, 18. Okay, and so we have to evaluate the norm of this vector also, and so that's going to be the absolute value of this times the norm of this vector right here. We have over 400 e to the minus 43 times the square root of 2 squared plus minus 3 squared plus 18 squared. Okay, and so we can cancel this part of it, 324. So 324 plus 4 plus 9, so 337. So we have minus 1 over the square root of 337 times the vector 2 minus 3, 18, which will be a unit vector. All right, so part 3, find the maximum rate of increase at P. So that's just the norm of grad T at P. And so this will be just 400 e to the minus 43 times the square root of 337. Okay, question 12. So this question says, find the equation of the tangent plane to z equals y squared plus cos x plus y at the point P. Now, the formula for tangent plane is z minus z0 is equal to x minus x0 f subscript x at P plus y minus y0 f subscript y at P, where P equals x0, y0, z0. And so in this case, here's our x0, here's our y0. The z0 value requires us to sub in these two into our function to find z, or z0. Okay, so this is a three-dimensional version of this point right here. So let's go ahead and calculate this. So f of pi on 2, 0 is 0 squared cos of pi on 2 plus 0. And of course, this is just 0. So z0 is 0. Okay, and so also we have x0 is pi on 2 and y0 is 0. So our formula then says z minus 0 is equal to x minus x0, which is pi on 2, f subscript x at P. Well, we need to calculate the partial derivative of f with respect to x. And so let's get out some separate paper and do that. Or let's see, maybe we can fit it in here. So let's try to fit it in here. So f subscript x is y squared times the partial derivative with respect to x of cos of x plus y. So we need the chain rule for this piece. And so let's let u be equal to x plus y. So we differentiate cos of u with respect to u. and multiply by the derivative of u with respect to x. So the derivative of cos of u with respect to u is minus sine of u. So we have minus y squared sine of x plus y, and then times the derivative of x plus y with respect to x, which is just 1. So f subscript x is minus y squared sine x plus y. Okay, so that goes here, but we sub in the value of p. So we have minus 0 squared sine of pi on 2 plus 0. Okay, of course, this will be 0. Now, we next add y minus y0. So y0 is 0. And then we need to calculate f subscript y. So f subscript y is... Now, this requires the product rule because we have a y here, we have a y there. These two functions are multiplying together. Okay, and so we have y squared times the derivative of cos of x plus y with respect to y, which is minus sine of x plus y. And then we swap the roles of these, so plus cos of x plus y times the derivative of y squared. And so that is plus 2y cos of x plus y. Okay, and so now we sub in our y value and our x value into this function, and so we're going to get 0 because y 0 is 0. So 0 there, just times 0. And so here then we have x minus pi on 2 times 0, y minus 0 times 0. Both of those are 0, so they add up to 0. So we just have z equals 0 is our tangent plane at the point P. Question 13. Find and classify the critical points of the function f of x and y given by 8xy minus a quarter x plus y to the power of 4. Okay, so the critical points occur when grad f is equal to the 0 vector. So we need to calculate fx and fy. So fx is the partial derivative with respect to x of 8xy minus a quarter x plus y to the power of 4. And so the derivative of 8xy with respect to x is 8y. Then we have minus a quarter times the derivative with respect to x of x plus y to the power of 4. And so now for this, we need the chain rule where u is equal to x plus y. Okay, and so the derivative of u to the 4th with respect to u is 4u to the power of 3. So we have 8y. Now 4 times a quarter is 1, so minus u, which is x plus y, to the power of 3. And then times the derivative of x plus y with respect to x partially, which of course is just 1. So we have 8y minus x plus y to the power of 3. This is our f subscript x. Now similarly, f subscript y is going to be 8y minus x plus y to the power of 3, because this all works out, oh hang on, no, this will be 8x. Okay, so this all works out just the same way, except down here we have a y, and so that would still be, in this case, equal to 1. Okay, so now we have the components of grad f. Grad f is equal to the vector 8y minus x plus y to the power of 3, comma 8x minus x plus y to the power of 3. Okay, and so grad f is equal to the 0 vector when we have the simultaneous system of equations 8y minus x plus y to the power of 3 equals 0, and 8x minus x plus y to the power of 3 equals 0. Okay, and so if this system, or these two equations, are simultaneously true, then we can subtract one equation from another and get 8 outside of y minus x equals 0. So we must have y equals x. Okay, and so we can take this y equals x now, substitute that into one of the equations, say the first one. So replacing y with x everywhere, we get 8x minus 2x all cubed equals 0. So that is 8x minus 8x cubed equals 0. Now factorizing this equation, we have 8 outside of 1 minus x squared times x equals 0. And so we see all of the possibilities here are x equals 0, or x equals minus 1, or x equals plus 1. These are our possibilities here. So this gives us 3 critical points. Since y equals x, we have the critical point 0, 0. We have minus 1, and we have 1, 1. So these are our 3 critical points of that function. Now to classify these, we want to use this theorem right here. It says assume partial derivatives exist and are continuous at the point AB, and AB is critical. Okay, so if fxx is positive and delta is positive, we have a local minimum at that point AB. So you can see we need to calculate fxx and we need to calculate the determinant of the Hessian matrix. Okay, so fxx is the derivative with respect to x of fx, which is the derivative with respect to x of 8y minus x plus y to the power of 3. And so differentiating 8y with respect to x partially, we've got 0 for that. And then differentiating x plus y to the power of 3 with respect to x partially, the 3 comes down. So we have minus 3 x plus y to the power of 2 times the derivative of x plus y with respect to x partially, but that's just 1. So we see then that fxx is minus 3x plus y to the power of 2. Okay, so we also need, in our Hessian matrix, we need fxy, which is the partial derivative with respect to y of f subscript x. And so this is derivative with respect to y of 8y minus x plus y to the power of 3. So here we have 8 minus 3 x plus y to the power of 2 for fxy. Now, this should be the same as fyx by Clairaut's theorem, but let's calculate this anyway. So we have the derivative with respect to x of f subscript y, and f subscript y, we previously calculated this to be 8x minus x plus y all cubed. Okay, and so we get 8 minus 3x plus y to the power of 2, which is what we have here. And then finally, we need fyy. So this is the derivative with respect to y partially of fy. We're differentiating 8x minus x plus y to the power of 3. So for this part, we have 0. Then for this, we have minus 3x plus y to the power of 2. And this is fyy. Okay, so now we can form the Hessian matrix. So I'll just use the letter H for this. So fxx is minus 3x plus y to the power of 2. fxy, 8 minus 3x plus y to the power of 2. fyx was the same. fyy is minus 3x plus y to the power of 2. And so next we need the Hessian at our point of interest here, which was, it's at our critical point. So Hessian at 0, 0. So we just sub in 0 and 0 for x and y. So we have 0 for this, we have 8, and we have 0. Okay, and so delta is the determinant of our Hessian. But let's write delta at 0, 0. And so we have 0 minus 8 times 8 is 64, and that is negative. So fxx at 0, 0 is equal to, right here, it's just 0. And so now we should be able to classify the critical point 0, 0. So let's have a look according to this page, or this theorem right here. Fxx at 0, 0 is 0, but delta at 0, 0 is negative. So our third item there says that 0, 0 is a saddle. Okay, so let's repeat this with our other critical points. So we had a critical point -1, -1, and a critical point 1, 1. So let's start with -1, -1. So our Hessian matrix, now just substituting into this matrix, we have -2 gets squared, and that's 4. So -3 times 4 is -12. And then 8 minus 12. And then again, 8 minus 12. And then here we have will be -12. All right, and so taking the determinant of this one, so delta at -1, -1 is the determinant of this matrix, which will be 144 minus, now this here is -4, so -4 times -4, 16, but we have a minus in front of it, so -16 there. And so then we have 128 for that, which is positive. Okay, similarly, because all of these are squares in here, it will be the same thing at the point 1, 1. So delta 1, 1 is also 128, which is positive. Okay, so finally fxx at the point 1, 1 is minus 12, and that's the same as f(xx) at -1, -1. Both of these are negative. Both of these are negative. Okay, so according to the theorem here, f(xx) is negative, delta is positive, so we have a local maxima at the points 1, 1 and -1, -1. Okay, so now that we have all of that, let's go and plot this function using Mathematica. Okay, so I'm going to run that. So here's what this looks like. And so in the middle there, we've got the point 0, 0. So you can see it's a minimum one way and a maximum the other way. So that's what a saddle is. And then we have local maxima at the point 1, 1 and at the point -1, -1. So you can kind of see those. It looks like here and here. Okay, question 14 says, find the maxima of minima of the function 5x squared plus y squared subject to the constraint x squared plus y squared equals 1. So this is the unit circle. So it would make sense to draw a little picture of this. Okay, and so here I've drawn a rough sketch of the constraint. But then this is just the xy plane here. So through that we have a surface z equals f of xy. And we want to find the maxima or minima of this surface given that x squared plus y squared is equal to 1. All right, so this is a Lagrange problem. So what we do is we let g of x comma y be equal to x squared plus y squared minus 1, taking that 1 over to the left-hand side. So this equals 0 where the constraint holds. Okay, and so the equation of interest here is grad f equals Lagrange multiplier lambda times grad of g. Okay, and so we need to calculate grad f, we need to calculate grad g. So f subscript x is the derivative of this with respect to x partially, which is 10x. F subscript y is 2y. G subscript x is 2x. And g subscript y is 2y. All right, and so this equation is the vector equation 10x to y is equal to lambda times 2x to y. Okay, so expanding this out and forming two scalar equations from this, we get 10x is equal to 2 lambda x and 2y is equal to 2 lambda y. So that's a system of simultaneous equations. Okay, and so we have a choice here. We can solve for the constraint or we can eliminate the constraint. So let's rearrange this first equation. So we'll have 2x outside of lambda minus 5 equals 0. And then the second equation, if we take this over to this side and factorize, we have 2y outside of lambda minus 1 is equal to 0. Okay, so for this to be true, we could have x comma y is 0, 0, or if lambda is equal to 5, then this equation gives 0, so that equation holds, but this one would say 2 times 4 times y equals 0, and so then y equals 0. Now substituting into the constraint, so we say and using x squared plus y squared equals 1, if y is 0, then x is plus or minus 1. And so we have the point 1, 0, the point minus 1, 0. Okay, now if lambda is equal to 1, the second equation gives 0. And so then we would have to have x equal to 0. And so using the constraint, we have y squared is 1, so y is plus or minus 1, which gives the 2 points 0, 1 and 0, minus 1. Okay, now this point 0, 0, this does not satisfy the constraint. So let's put over here, note 0 squared plus 0 squared is not equal to 1, so 0, 0 does not satisfy the constraint. So we have only the 4 points of interest here, and let's find these on our diagram. So this point, this point, this point, and this point. Okay, now at these points, we could have f being a max or a min. So what we want to do here is sub those points into f to find out whether we have a max or a min. So f of 1, 0 is 5 times 1 squared plus 0 squared, which is 5. F of minus 1, 0 is 5 times minus 1 squared plus 0 squared, also 5. F of 0, 1 is 5 by 0 squared plus 1 squared, which is 1. F of 0 minus 1 is 5 times 0 squared plus minus 1 squared, which is 1. Now, which of these are the bigger and which are the smaller? So 5 is greater than 1. So since 5 is greater than 1, we have plus or minus 1 comma 0 give maxima, and the points 0, 1, or 0 plus or minus 1 give minima. Okay, so let's go back to our diagram. So these are min here, and these give max here and here. Okay, and so this completes question 14 part A. So now 14 part B says find the global max and minima of f over the unit disk. X squared plus y squared is less than or equal to 1. So that's inside here together with the boundary. So it helps to know what's going on the boundary, which we already have. Okay, so part B. So for this, we need to calculate grad f and solve for the points x, y where grad f is 0. So grad f, remember, was the vector 10x, 2y, and this is supposed to be equal to 0, 0 where we have critical points. And remember, critical point means it's either the top or bottom of a pyramid shape, so sharp point, or a point where the tangent plane is horizontal. Okay, so solving this equation right here for x and y, we have the unique critical point 0, 0, because 10x equals 0 whenever x is 0 and 2y is 0 whenever y is 0. Okay, and so now let's identify this on our diagram right here, but we need to evaluate f at that point 0, 0 and compare it against our boundary in order to find global max. Okay, and so f of 0, 0 is 5 times 0 squared plus 0 squared, which is 0. So here we've got 0. The maxima that we found were 5 and the minima were 1. Okay, so let's classify the critical point 0, 0. So to classify, remember, we need fxx at 0, 0. So fxx is the partial derivative with respect to x of fx, and so we're differentiating partially 10x, and so we get 10, and that is positive. Okay, and so let's have a look at that theorem there. So for this to give a local minima at 0, 0, we need that Hessian to be positive. So let's calculate our Hessian matrix and then its determinant. And so now we need fx y, so differentiating with respect to y, 10x, we get 0, and similarly fyx gives 0, and fyy is 2. So the Hessian is the matrix 10, 0, 0, 2. Okay, and so taking the determinant of this, we have 20, which is positive. Okay, and so looking at our theorem here, fxx is positive and delta is positive, and so we have a local minima at 0, 0. So the point 0, 0 is a local minima. Okay, so finally, to determine global max and min, what we need to do is compare inside domain, so x squared plus y squared less than 1, with boundary of the domain, x squared plus y squared equal to 1. Okay, so what happens on the boundary? Well, we've got minima along that boundary of 1, maxima at 5, but inside the boundary we have a single critical point at 0, 0 giving 0. Comparing 0 with 1 and 5, we can see that the point 0, 0 gives a global minima, and the points plus or minus 1 comma 0 give global maxima of 5. Okay, and so this completes question 14 and hence the tutorial.